Good morning. Welcome to class, Krishna's class. Last time we introduced the complex inner product space, and then starting from R2 and R3, for which we have the geometry at our in front of us. We generalized to Rn over R, and then the next stage was whether we could use the complex vector spaces for this purpose, and we found that this essentially asks for a modification in the properties of the inner product, or what you call inner product has to be slightly modified. We modified it in such a way that in the case of R, the same definition works. So it is a natural generalization of what we have observed on real vector spaces. And just recall, so if you have on Cn over C, we define x equal to xn, y equal to or xi, yi, all elements of C. And Cn over C is a vector space with the usual addition and scalar multiplication. In this case, we define the inner product of x with y on to E3. We are using k here. One to k. In the real case, obviously, yi conjugate would become simply yi. So that is how we modified it. Now we don't have any more geometry to help you. Started with a geometric insight, generalized it consistently, and then further generalized to complex vector space Ck over C. We got the inner product defined or modified the way in which it is consistent with all other things like giving a norm, etc. etc. Okay, so that I have explained last time. Now what we do is the stage is set for making a very general inner product space or defining a general inner product space. So let inner product space. So let H be a complex vector space. That means C is the associated field. Now we define an inner product on H as follows. For X, Y belonging to H, an inner product on H denoted by is defined as a complex value function on H cross H with the following problem. So it's a complex valued function. That means for X, Y belonging to H cross H, the inner product X, Y is a complex number. It's a complex number. What are the properties? The properties, let us recall whatever is there and just write it down in the general notation. First one is Yx is equal to that is the first property. Second property is x plus y equal to that means it is additive in the first variable. Okay. The third property is that alpha x y, inner product of that, is equal to alpha times, and together 2 and 3 together means see x belonging to h Further, XX is non-negative. The next property. Greater than or equal to 0. H. And the fifth property is on this. If and only if now remember or just recall the property 1. Okay, that is the definition of the inner product. Okay, mark. One implies N. However, we would like to be non-negative. And hence okay. Further, we also need this, that this is equal to this is essential for defining a norm. Now let us look at some consequences. The first consequence is 0y equal to 0 H. This is the 0 element of H. Then you have, see, this is a consequence of 3. How does it come? You look at 3. This is alpha x y equal to alpha times inner product of x with y. Set put alpha equal to 0. Okay. And then you get this result. The second property is the map X Now this is the consequence of these two. Okay, that 2 and 3. A linear. In other words, x defines, sorry, y defines every y a linear function on h defined by say xy. So fy is a linear function. Now this is easily proved that actually the properties 2 and 3 you see, first of all, you see that fy is a function from h. See, C is linear by 2 by 2n. It's a linear function on. Okay. So every element of the space H defines a linear function on. Now the third property is alpha conjugate. So when the scalar multiplication in the second place, then alpha comes out with a conjugation. So this is what you have, and this is something which you can easily prove, because you see that conjugate so that's a proof for that, and that's very simple. Further, D, one can easily prove likewise, playing around with it. Equal to So zxy is linear in the second way. Sorry, is additive in the second way. It's not linear. That is additive. The second variable. And conjugate additive, conjugate linear, in the second way. One can easily prove this. This is for every alpha, beta belonging to C and X, Z. So this is these are the properties that you have for this. Now we shall introduce the norm. We are all generalizing or developing everything based on our experience of working in CA. Okay, so define carefully. This is definition. The norm on X fine. Fine. And you see that this is for every X belonging to X. Now you see that by the properties 4 and 5, this is certainly positive. Let me define it this way. By 4 and 5, we have the inner product of X with itself as non-negative, and then you take the square root of that, you take the positive square root of that, and call that the norm of norm. This you see is obtained from our experience of working on CA. Okay. Now for the norm, we have the following nice properties. Now the inner product has the following nice properties, which is again something that we have obtained from our experience, and one has to prove this generally. So let me write that. This is what's called the famous Cauchy-Schwarz inequality, or sometimes simply Schwarz inequality, and which is in the real case of R2 and R3, we have identified this, defining the angle between the vectors x and y. So we shall this is a very important inequality. xy belonging to H. This is the so-called Schwarz inequality. Identified xy as a measure of the angle of between the vectors x and y, in the sense cos theta. Therefore, consequently, and we have the inequality this is the primitive of the Cauchy-Schwarz inequality. This is a very important inequality. So it works in the same form with the same notation. So in the case of R2 or R3, this simply reduces to our result that mod cos theta is less than or equal to 1. Okay, so that is the connection that you, geometric connection that. So now we shall prove this theorem. So this is a remark I have here. So we will prove it. It's also called a Cauchy short. And C equal to term of I square. Now there exists a complex number alpha such that mod alpha is equal to 1 and alpha times inner product of y with x. This is equal to, this is inner product of y with x, not x with y. Or if you want to write with x with y, then you have to conjugate them. Okay, so alpha is so different. I mean, such an alpha exists. That is simple. Then, for every r belonging to R, inner product of R x minus R alpha y, or in other words, it is going to be something non-negative. This, if you use the properties of inner product and expand, then this becomes xx minus R alpha yx minus R alpha conjugate xy plus R square here we have used the fact that mod alpha is equal to 1 in the last question. Now that is in terms of ABC, A minus 2BR plus CR square is greater than or equal to 0, because you see that this is the inner product of a vector with itself which is greater than or equal to 0. This is greater than or equal to 0. Therefore, you get this relation. So we have in fact hit upon the right kind of properties for defining the inner product. That's what is getting clear. So if C equal to 0, suppose it is not true, otherwise the inequality fails to hold. For large values of As you see this is for every R belonging to R. So for large values of R, this would fail. Therefore, if C is equal to 0, then B is fail. If C is positive, then take R equal to B by C. That is well defined. Then you obtain that is you see that this is equal to taking the square root, positive square root. Now suppose AC. Then we have why suppose note that this quality holds in Schwarzschild. If and only if x is equal to beta y and this is what we have. See, if you go back to your R2 or R3 where you have a visual perception, there you see that this becomes, see, I'll make this remark, important remark. See, in R2 or R3, equality holds in the Cauchy-Schwarz inequality. If and only if cos theta is equal to 1. That means theta equal to 0. cos theta equal to plus or minus 1. Fine. That implies because you see that this is x, this is see the two cases can occur. Mod cos theta equal to 1 means cos theta equal to plus or minus 1 when theta equal to 0 or theta equal to pi. In either case, you can see that this is geometry. Okay. So the situations are theta equal to 0 is this is x, or theta equal to 0 or theta equal to pi. So these are the two situations. This corresponds to theta equal to 0. So x is a scalar multiple of y, or x is a it's a scalar multiple of y. Maybe positive or negative depending on whether theta is equal to 0 or pi. One of the consequences of this is triangular inequality. Belong into H. Norm of x plus y so the proof is very simple. Use Cauchy-Schwarz inequality. Plus y, and this is equal to y and this is less than or equal to because this will become the real part of the inner product of x with y. That is was less than or equal to modulus of inner product of x with y, and that there you use Schwarz inequality. Here you have used that this is what we have used. Okay. Now this is equal to therefore this inequality. Therefore taking the positive square roots, in fact our this Schwarz inequality is a tool to prove these kind of results. Okay. Now having got this length function, okay, we now define the distance function. Definition. Then we can prove that D is a metric. That is HD is a metric space. Okay. That's quite easy to prove. Verify this. So, of course, dxy is positive. And this is proved for the norm. And then, of course, we have using this, we have now you can prove this dxy that is clear. Okay, that is norm of x minus y equal to norm of y minus. The third property that you have to prove is this. You have to prove this. So the triangular inequality. Now dxy let us prove this. This is the triangular inequality. Geometric space. So you can, it's a topological space, therefore you can now do analysis on it. So it's a inner product space, therefore it's a normally linear space, therefore it's a metric space. Okay. So H is a metric space. Now we shall define completeness. We can talk about completeness. All Cauchy sequences converges so you can give the definition of this. I mean, it's not difficult. Given epsilon positive, there exists an n such that see, this is a Cauchy sequence. Okay, Cauchy sequence. Then you have epsilon positive, there exists a n such that now this is what you mean by Cauchy sequences. Now if all Cauchy sequences are converges in X, then you say it's a complete space. So that is the completeness. Now we are in a position to say what a Hilbert space is. A Hilbert space a complete inner product space. This is the definition of the Hilbert space. Otherwise, we will simply call it an inner product space. I will give you some examples. Is a inner product space. Defined by this, where x equal to and one can also prove that straightforward to prove that is a Hilbert space. See, what you prove, what you use is use the completeness of see. So you can prove that it's a Hilbert space. I am not going to. Second example is this. measure space. L2, that is the equivalence class of all complex values fine. Now we have seen that LP is consider LP space LP, and this is the special case where P equal to know that prove that LP is complete. Because now on L2, the inner product one can easily verify that this is in and half. the inner product. Now L2 is complete. In fact, it follows from and this is a special case of that. Therefore, this is complete. Okay. Therefore, L2 mu is a we take up a third example. State x to be equal to the interval 0. Consider valued continuous functions. Then fg this is an inner coefficient. This is an inner coefficient. But this is not. We have already explored this particular space in the case of L. Therefore, this is not complete. It is not a Hilbert space. Okay, let me make some remarks about how you come across the particular definition of the inner. Okay? So that is what I am going to. It looks totally disconnected, CL. At the outset, disconnected. But this is not. So see, this is actually in the path of developing these ideas. Okay, in CEN we had X theta k. See, we invent this as functions. So we take x be equal to k. On this, we define the function. Then you see that yeah, now we define taken x to be this. It's a positive measure. Okay. Therefore, using that, one can rewrite the whole thing as sigma xi this is equal to integral over x conjugate. Is a counting measure. Therefore, this is the integral that you have. Okay. Or you can write here x t y conjugate. T runs over okay. Now this is the one. Therefore, you see that the general inner product that we have defined so what you are doing is you are taking x at t, multiply it y conjugate at t. Doing the same thing. Now, general measure stays. The positive measure. We have just mimic that. This is how this comes. Okay. So if you take here x to be interval 1 to k, right? So you see that this is a generalization. If you take x to be, so in this, if you take mu as the counting measure, equal to dx, the set of all subsets of x, and mu as the counting measure, then we get, see, this is exactly equal to integral over x dv. So there is a unification of all these ideas. So how this particular choice of the inner product in this form came in the general case is clear if you identify what is happening on CK. Okay, thank you very much. So that completes our journey from vectors to L2D. Thank you very much.